Now, logarithms have several applications. And one application we're going to look at right away is how to use them to solve exponential equations. So before we do that, we have to introduce another property of logarithms. Now, there are more properties coming in the next section, okay? But this is another really important property that we want to remember for logarithms. And other than rewriting a logarithm into exponential form, this is probably the most common thing we'll use. In particular, I'm thinking in calculus. So the property of logarithms say that if you have log, wow, there should be an O, log base b of x to the y, we can bring the exponent to the front. And that is the property that's going to find us very useful when we're solving exponential equations. We can actually take an exponential and bring it to the front. Realizing that my subscripts are not very small. I should probably write a little bit bigger then. So they look smaller. There we go. Good enough. And a bigger X. Okay. So let's rewrite this example using the exponent property here. So first thing I'm going to do is I'm going to rewrite 1 over x squared as x to the negative 2. I don't really care about the natural logarithm. That's not what's exciting here. Okay, I can just leave that alone. I don't need to write log base e or anything because I'm not going to simplify this. What I am going to do, though, is take that negative 2 and bring it to the front. And there you go. That's the rewritten version of this logarithm. I can rewrite it as negative 2 natural log of x. And these two are equivalent. They're the same thing. But this one's a lot prettier, right? Just negative 2 natural log of x is a lot better to look at than the one with the fraction. Okay. One other property that's used, but this isn't as big of a deal. It's useful, and I'll show you some examples of where it's useful. But this is more used to do some proving that's kind of useful to us. All right. So it's called the change of base formula. And here's the idea with the change of base formula. This is going to be super helpful for us when we want to evaluate something that isn't the natural log or the common log. In other words, we want to put it in our calculator, but we don't, it's not the natural log or the common log, which is what's on the calculator. So the change of base property says this: if you have log base b of x, it can be rewritten using any other base we want as log base a of x over log base a of b. So we can take any other log we want and just rewrite log base b of x as log base a of x over log base a of b. So the same log in the numerator and denominator of the x and then of b. Now let's see how this can be useful. So for instance, let's say we want to find log base 2 of 10. I'd like to use my calculator. And on my calculator, I have the common log and the natural log. So I could rewrite this if I wanted to as log base 10 of 10 over log base 10 of 2. Now, by the way, I wouldn't write the base 10. The whole point of doing common log is to not write the 10. So this is just the log of 10 over 2. I don't know why I'm putting parentheses. I guess because they have the parentheses on the original. And 2. And I can plug that in the calculator. I can find the log of 10 and divide it by the log of 2. So if you plug those into the calculator, and I would do it all at one time. I would do log of 10 divided by log of 2 all at once. And I get 3.322. Here, we'll round it to 3 decimal places. Now, I could have used any log I wanted to. I could use the natural log. In fact, take a second and do the natural log. Let's take the natural log of 10 over the natural log of 2. So using log base e instead. And do it on your calculator. Natural log of 10 divided by natural log of 2. And I'm literally plugging this in my calculator while I'm saying this, and you get the same answer, which is the point. Doesn't matter what log you use, as long as it's the same on top and bottom, it'll be an equivalent statement. And that's nice for us to use if we want to plug something in our calculator that isn't in the bases that we normally work with. Okay, now that's nice. Change of base property. The properties with the exponents, those are all nifty, but how does that work with solving equations? Well, let me show you. So let's say I want to solve this equation, 2 to the x equals 10. 2 to the x equals 10. So there's no way for me to solve this because there's nothing that I can raise to 2. There's no exponent that I can plug in there that's going to equal 10, right? If it had equaled 8, I'd say 3, right? But it doesn't. Okay, so here's where we can use logarithms. What I can do is take the log of both sides of the equation. So let me put that over here. Take the log or natural log, doesn't matter, either one, of both sides of the equation. Both sides of the equation. And what that allows me to do then is to take the exponent that's on the 2 and bring it to the front using that property for exponents. So use log exponent property. And here I'm going to abbreviate that entire sentence. Use log x prop. Okay, now here's why that's useful. I just realized, by the way, I accidentally put an x instead of 10. And it's not wanting me to erase for some reason. There, now it's letting me erase again. Weird. So that should have been 10. Sorry about that. Okay, so now I can solve for x by dividing both sides by log of 2. And that is something I can plug into the calculator. I can find the log of 10 over the log of 2. So I'm going to take the log of 10, divide by the log of 2, and we get what we got earlier, 3.322. That's funny. I think the author did that on purpose. All right, so there you go. We were able to solve this exponential. If you take 2 and raise it to this power, this disgusting decimal, we're going to end up with 10. Pretty nifty. All right, so let's look at it in a more complicated setting. Let's say we are wanting to use the example of how India is predicted its population is going to look like, okay, in years after 2008. So this is the equation predicting that based on growth rates and everything else. Okay. Let's figure out when this thing is going to equal 2 billion. Okay. Now, this particular model actually is calculating in the billions. It actually says that, right? In billions. So what I want to do is I want to figure out when this equation, 1.141 plus, okay, so here, rather than write the plus, I'm going to put 0.0134. I'm just going to add the 1 and the 0.0134 to the t. We want to know when this thing is going to equal 2 for 2 billion. And this is what I'd like to solve. Okay, kind of gross, but let's do this. So here's what we're going to do. We're going to go ahead and divide by 1.14. And the reason is I'm going to isolate the exponential part of this equation. So 1.0134 to the t equals, okay, now you can plug this into your calculator. It's going to be gross, but you could also leave it in fraction form and we can plug it in the calculator in a little bit because we're going to end up plugging in a log in a second. Okay. So I plugged it into my calculator just to see what a decimal approximation it would be. And I got 1.42857. And I would use as many decimals as you can muster writing because the more decimals you use, the less you'll have to worry about your rounding being different. Okay. Okay, so now in order to get t no longer as an exponent, I'm going to take the log of both sides. Now I used the common log earlier, but I'm going to use the natural log now because it really doesn't matter which log we use. As long as you take a logarithm of both sides. So I'll just use the natural log. In fact, as an FYI, a lot of math people like to use the natural log opposed to the common log when you're given a choice, just because it's literally less letters to write and they're that lazy. Oops, that's not a 4. That's supposed to be a T. Okay, so now let's bring the T to the front. 1.0134 equals the natural log of 2 over 1.14. Okay, and now to solve for T, I'm going to divide both sides. And this is what I'm going to plug in the calculator. It's gross, but I can handle it because I just need to make sure that I plug it into the calculator. And you may want to do it in steps, but get it all plugged into the calculator. So the natural log of 2 divided by 1.14 divided by the natural log of 1.0134. All right. And oops, I just realized I made a mistake. Plug something in wrong. I plugged a 1 over 1.14 instead of 2 over 1.14. Man, that made a huge difference, just so you know. Okay, so I ended up with 4.2. I'm sorry, 42.2. So 42.2. And this would be years. This is how many years it's going to take. So in the year, so it's plus 2008. So in the year 2050, it's going to achieve a population of 2 billion. Oh, okay. So there you go. That would be the conclusion of when that would happen. Okay, so let's try another one, another equation to solve. So we're just going to keep practicing using logarithms to solve equations here. So since I've already kind of let you know that we like natural log, we favor natural log, I'm going to probably use natural log from here on out, but you can use log. There's nothing wrong with that. Okay, first thing I need to do is I need to isolate the exponential. So I'm going to divide both sides by 5. And 2/5 is actually not a bad decimal. So I'm going to go ahead and just write 0.4. But you can just leave 2/5 if you want, just like we did in our last problem. You can leave it as a fraction and plug it in. Okay, so now I'm going to take the natural log of both sides. And I'll go ahead and introduce parentheses here to make it a little bit cleaner. I'm going to bring the exponent to the front, which is the whole point. And now I can solve, sorry, that's a 3, for T by dividing by, not only by the natural log of 1.07, but also by the 3 in the front. Both of those will cancel and it'll leave me with T. Now, be careful when you plug this into your calculator. You might need to put an extra set of parentheses around that denominator because of the 3. The 3, you have to make sure you tell the calculator the 3 needs to be part of the denominator. Otherwise, what it'll do is it'll take the natural log of 0.4, divide it by 3, and then times the whole thing by natural log of 1.07. So make sure you put parentheses around that. All right, let's enter it into the calculator. And if you enter it correctly, you should get negative. Here, let me write. T equals negative 4.514. I don't know why I chose to go to 3 decimals. Why not? 514. Sorry, it was hovering in the air. Kind of weird. That's a weird looking T. Let me fix that. Boom. All right. There you go. Okay, so now let's look at some examples where we're going to kind of build on what we've talked about previously. So let's say a population grows from 100 to 130 in 2 weeks. Find the continuous growth rate. So this saying continuous growth rate is implying that we want to use the E equation we talked about previously. Let me write it in blue. The model for the E equation, which would be here, we'll call it P of T for population in terms of time equals A E to the RT. So that's the model we'll use for growth rate. Okay, so let's plug in what we know. We know that the population equals 130. It started at 100, and we know that happened in a 2-week period. So I'll plug in 2 for T. All right. So I want to solve this equation. Nice. We can do that. Let's divide both sides by 100, which is going to give us 1.3. And then here, I'm going to write that as 2R instead of R times 2. And now let's take the natural log of both sides. And then we can bring down the exponent, but a magical thing happens. When you take the natural log of E, it disappears. Remember, they cancel. Those two are inverses of each other. So this is actually just 2R, just the exponent. That's nice. If you forget, it's okay. You could just keep the natural log of E and solve and plug into your calculator. Your calculator is going to go, oh, that's a 1. But it's nice to notice that the natural log of E does end up canceling out. And then to solve for R, I divide by 2. So this is what I'm going to plug into the calculator. Wow. The natural log of 1.3 divided by 2. And I get 0.1312. Okay, so as a rate, that would be 13.12% growth rate. I think that's what they wanted. Find the continuous growth rate. Yep. Boom. That's it. That's what they wanted. So we found the rate of growth based on the continuous growth rate model. All right, let's look at some more useful information. This idea that we have a continuous growth versus what we call the standard exponential. So we have 2 models for growth. We have the model where we do the 1 plus R, and then the model where we use E. So these 2 models are equivalent, and we can solve or set them equal to each other and realize that really what we're saying is that 1 plus R equals E to the K. And they give some names to this. So the original equation is called the periodic growth rate. That's percent growth by a time period. And then in that equation, the second equation, K is what's called the continuous growth rate. And you can convert between those using 1 plus E equals E to the K. Okay, so let's try to find or use this in an example. So let's say this particular company uses a continuous growth rate model. What if we wanted to know what the annual growth rate was? Okay, so to do that, based on what we have up here, I'm going to take E to the K. So in this example, E to the K is E to the 0.12. Wow, that's a decimal. And I'm going to set that equal to 1 plus R. And that's going to give me, or if I solve this for R, that'll tell me what the growth rate is for annually for this company. So I'm going to minus 1 from both sides really quick. And that's what I'm going to plug into the calculator. I'm going to plug in E to the, where's my E? E to the 0.12. And then I'm going to subtract 1 from that. And that gave me 0.1275, which as a percent would be 12.75%. So that's the annual growth rate for this company who was using an exponential growth model or continuous growth model.